Yeah, so this walkthrough is a primer on probability distribution. So what I've done as part of this tech is that I've taken two distributions, which is binomial and normal distribution, and walk through their characteristics with some examples. And the reason for picking this up as one of the topics for posting is that a lot of folks who get into readings on VAR or portfolio optimization, risk reduction, diversification, and so on and so forth would come across these terms as part of the readings on these subjects. So it's important to get a handle on what exactly these mean when you get into some of the topics which are downstream in nature. So let's start with the basics. So the first thing you need to know is that concept of frequency distribution, which basically lists all outcomes of an experiment. So you could, or a survey. So for example, you could take a class of 15 students and then slot them into different buckets based on their weight. And that becomes a frequency distribution. Following through this frequency distribution is what we call a probability distribution, which is related to frequency distribution in that it tells you how outcomes are expected to vary. So it's extremely useful when you want to make decisions in an uncertain environment, which we will see as we go through this walkthrough. So let's start with a fundamental example, and this is widely used in most of the textbooks of statistics to explain the concept of distribution. So you have two coins, fair coins, on which you're going to do two tosses. So the first toss can be a tail and a tail, which is basically two tails with a joint probability of zero point 0.5 into zero point 0.5, which is 0.25. You could have a tail followed by a head, which means the resultant is one tail and a joint probability of 0.25, following with the other two possibilities, which is a head and a tail and a head and a head, both of them also having a probability of 0.25. Now all the probabilities add up to 1. So you can plot these as a frequency distribution. So the probability of getting one tail is in two of the outcomes, which is tail and head and tail. Therefore, the probability of that becomes zero point 0.5, which is 0.25 plus 0.25. The probability of no tail or two tails is 0.25. So that is represented by the other two columns, which are to the left and right of the central probability of zero point 0.5. Now this looks like a fairly good distribution, mirroring what we could call as a normal distribution, which we'll understand in more detail in the subsequent slides. One important point is that probability distribution can either be discrete or continuous, and this term is something which you will frequently come through when you read articles and books on this subject. Now, discrete distributions are basically those which have limited set of values, and continuous distributions, to the contrary, can have any value within a range. For example, the probability that you were born in a given month is discrete because there are only 12 possible options. On the other hand, if you're measuring in an experiment effluent particles in water, which is basically particles per million, that can have any reading. So therefore it is continuous in nature. Now what is a random variable? A random variable is a variable that takes different values as a result of outcomes of a random event. Like distribution, random variables can be discrete, which means they have a limited set of values, or continuous, which means they can take any value within a range. For example, there could be a clinic in a town which does not know today how many patients will turn up tomorrow. So number of patients is a random variable. Number of patients can turn out to be very high because there is a general virus or flu around in town, or it could be very low because there is a thunderstorm which is expected, which sudden sun thunderstorm which comes about the next day. The past records show that the number of patients can range between 100 and 115. So this random variable is a discrete, which means it can take a fixed value between 100 to 115. Now going forward, you can plot this as a potential set of values and assign and calculate the frequency or the number of patients on each day over a 100-day period, and that's the result which you get in the second column. And then you can work out the probability, which is nothing but the frequency divided by the total. So for example, for the number of patients 102, it will be 2 divided by 100 or point zero 0.02. Having collated this data, you can prepare a distribution chart which is given to the right, which tells you based on the y-axis, which is the probability, and the x-axis, which is the number of patients, what the distribution of patients with the associated probability looks like. One logical extension of what we did in the earlier slide would be to calculate the expected value. Now, what is the expected value? In this particular example, is the number of patients multiplied by the probability. So, for example, for 100 patients with a probability of 0.01, the expected value is 1. You can do this for the other observations as well, and the total comes out to be 108.13. What does this mean? It means that over a long run, the number of patients on a daily basis should average about 108.13. One thing to keep in mind is that more frequent common occurrences are given more weight. Let's take another example. You have a stock market investor, Bob, who's examining the possibility of investing in a stock called IDM. He's had a look at the historical data and slotted the return basically in 5 buckets, which is 0, 10%, 15%, 25%, and 50%. Based on the frequency, like what we calculated earlier, he's got the probability of zero point 0.2, 0.25, all the way up to zero point 0.1, and all the probabilities will add up to 1. So expected value will be return times the probability, which adds up to 15.75. So the question is, will Bob invest in this stock? So the answer is yes, because the expected value of the return, which is 15.75%, is higher than his threshold of 10%. Now, a couple of things on binomial distribution from a theoretical standpoint. It's widely used, primarily in the case of data which is discrete in nature. The origin of this is from that of a Swiss mathematician called Jacob Bernoulli, and the tossing of the fair coin is known as the Bernoulli process. So notationally, there are a couple of symbols. P is the probability of success, Q is that of failure, which basically is 1 minus P, R is the number of desired successes, and N is the number of trials. So the probability of R successes and N trials is NCR P raised to the power of R, Q raised to the power of N minus R. NCR being factorial N by factorial R times factorial N minus R. Going back to our example of tossing a coin, so what is the probability of 2 heads in 3 tosses? So N is 3, R is 2, P is 0.5, and Q is 0.5. So probability of R equal to 2, once you plug in these values into the formula, works out to 0.375. So probability of getting 2 heads in 3 tosses is 0.375. You have to keep in mind the binomial distribution mean is given by NP and standard deviation is given by square root of NP cube. Now let's take another example. So in a high school you have five students and there's a probability of zero point 0.4 of a student coming late. So P is zero point 0.4, Q is zero point 0.6, which is 1 minus zero point 0.4, N is 5. So you can build a binomial distribution based on this data. Students being late, number of students 0, 1, 2 can vary up to 5. NCR is how we calculate, which is basically 5C R, which is 5C 0 in this in the first case, followed by 5C1, followed by 5C2, and so on and so forth. P raised to the power of R and Q raised to the power minus R. The second part of the formula is given in the third column, so product you get is this. So probability of three students being late on a given day is 0.230. You can put this across as a histogram chart, frequency chart, and you get that what you have on the slide on the right side. Remember that if P is zero point 0.5, then the distribution is symmetrical. Although in this particular case, the distribution appears to be slightly skewed to the right. You can also use an Excel function called binom dist. And how to use it? The first term equal to binom dist is r, comma n, comma p, and the last you can give default equal to 0. So for example, if you want to calculate the number of students being late equal to 3, it will be binom dist parenthesis 3 comma 5, which is n, comma 0 0.4, which is p, comma 0, which is the default value. You get 0.230. Now, wrapping up on binomial distribution, keep in mind a couple of things. Number of observations is fixed. Each observation is independent and only two outcomes are possible, success or failure. And probability of success is same for each particular outcome. Only if these conditions are met, x as a variable can be said to follow a binomial distribution with parameters n and p. So we stop here and follow this through with the second part. We will finally cover normal distribution.